Welcome to the advanced guide to laterally loaded piles. In this video, I'm going to explain the research paper that we published recently about a new method that we implemented in some of our software applications for the calculation, the determination of internal forces for laterally loaded piles in multi-layered soil. To be honest, there is a lot of different ways how you can do this, but before we start this presentation, I actually added some tool here to this website. This is something that you can download to play around with, and once you do this, what your Windows PC is going to tell you, I mean, you can only do this if it's a Windows PC, by the way, so if you do this, what can happen is that it gives actually a warning that this is not trusted software whatsoever, and this is due to the fact that we didn't implement a software certificate to this tool, mainly due to the fact that we don't make any money out of these like free software tools, and I don't see really the point for like paying like $300-400 a year just for a certificate so that this Windows alert doesn't pop up, because frankly I don't really care whether you use it or not. It's just something that we added in order for you to experiment with, to play around with. So if you decide to install this, you end up with a software that looks something like this, and you can play around with to understand, to get like a little bit of feeling of the math and of the principles that were discussed in this paper. So I will show you the interface really quick. We have a couple of interface sections here. We can save and load presets. We can restore the default resets. By default, you will have default presets. And what you're going to have is you have a pile settings here for a standard CFA pile, which is a round pile. You can also use it for precast piles, and you just have to change the moment of inertia for this pile. That's why we included this feature here. So you have the diameter of the pile in meters, we have the length of the pile in meters, we have the elasticity modulus or the Young's modulus in meganewton per square meter, and we have the moment of inertia in meters times 4. So if you have a square, and this is something that we didn't include here, we wanted to give you the chance to put in any sort of moment of inertia that you want. So anytime you have any sort of shape for any sort of pile, you can basically take the diameter, you calculate the moment of inertia yourself, and add it in here in meters times 4. So next up, we have the soil layer model. We included a maximum of 5 possible layers here. The way that it works, you have the height of a layer in meters, you have the elasticity modulus, the stiffness modulus actually, of the layer on the top side and on the bottom side. So this is the graph for the development of the stiffness modulus over the depth, so that you can create something like this. Obviously in the top, where basically the soil layer model starts, because you're at like the working level, so to speak, basically the stiffness is basically non-existent at this place, and it will develop over the depth. And to be able to do this and not only have like a constant stiffness modulus over the depth, we implemented these 2 values there. And this is something that you can input here in the software. So stiffness modulus at the top in kilonewtons per square meter, stiffness modulus at the bottom of the layer in kilonewtons per square meter. You have the density of the soil in kilonewton per cubic meter. You have the internal angle of friction, and you have the undrained shear strength in kilonewton per square meter. You can enable or disable layers as you wish, and in this standard settings we just have 4 layers. And the way that it works with the heights is, so you have the working level, which is 0, which is also the place where the pile length starts. So the pile head is always going to be at 0 of your soil layer model and going to 22 meters of depth. So you also have to recall this. If you add up all of these numbers, that should be bigger than 22 meters, so that the software can actually calculate. So that you don't have, so basically that your pile is in a completely defined soil layer model. If not, then it will probably don't generate any results. So the way that it works with the heights is you stand on the working level 0, then you have 2 meters of layer 1, then after that from 2 to 7 meters you have 5 meters of layer 2, then from 7 to 9 meters you have 2 meters of layer 3, and so on and so forth. And you can input all of the parameters of the different soil layers. Okay, cool. First, let's talk about the MK and the HK. MK is going to be the loading moment on the top of the pile. So the top of the pile will have a bending moment, and the HD or HK is the horizontal force that attaches at the top of the pile. So when we look at MK and HK and MD and HD, you need both of these values because you calculate the left part here, the verification with the stresses between the soil and the pile, and the calculation of the passive earth resistance in a characteristic stage and not in a design stage. And the rest is going to be calculated on the design phase. So you need both of them, that's very important. If you use only the design values and you use the design values also as the characteristic values, you're also always going to be on the safe side. The last thing that we have, and this is going to be really cool, and this is the main idea why we want to use this software, and the main benefit of the software is going to be that you can play around with a number of springs. So let's say we reduce this to 30 springs. What's going to happen is you see that this entire thing gets more and more edgy, right? And this is because of what's written in the paper and what we use here with the springs. Basically, the model looks somewhat like this. Like you have, like we have a vertical pile, and this pile is has bearings in horizontal direction, and all of these are going to be springs. And with this parameter, the number of springs, you can increase or decrease the number of springs over the depth. And the way that it works, it will basically, when you have the length of the pile, it will say divide 22 meters by the amount of springs, and then you will have like the n springs amount of slices of piles that will impact the soil next to it. Obviously, the higher that you go with the resolution, the more calculation power you're going to need, but also the higher the resolution of your results is going to be. And so this is very interesting for you to play around with, just to get a feel for how many springs you need and how also the results are going to differ. If you press the calculation button, it will take all the parameters of all of these pages, and it will create the calculation. And here what you're going to see is you see like a verification according to a European norm, the DIN EN 1997 1-1, which is the Eurocode 7 for geotechnical calculations. And this is very interesting because I haven't seen this in the United States yet, but this is a very interesting thing that you can do. Let's just go back to the calculation once more and increase the resolution once more, because we see it a little bit clearer. What it basically does is it takes a look at the passive earth resistance over the depth. And because this increases really strong, in this tool we basically introduced a logarithmic scale for the characteristic stresses. And what you also will see is the bedding of the pile against the soil. And you see that it has a very weird looking shape, and it's at first glance not really intuitive, but it's actually pretty logical that you will see here that there is these spikes to basically to 0. That's where they go, but because we have a resolution, obviously we're never going to be recreating full 0 here. But anyways, it's going to go full 0 at these points, and this is due to the fact if we look at the displacement, lateral displacement, this here is the 0, 0. At all these places where we cross the 0, 0 in the lateral displacement, obviously what we are going to expect is that we have 0 bedding, right? Because the pile is not moving against the soil, because there's no displacement, and then obviously we're not going to be having any sort of bedding there. And obviously we see that, I mean, this is a logarithmic scale, so this is decreasing, the bedding is decreasing quite drastically over the depth. We have like these recurring zero crossovers where basically we go from positive displacement to the right to negative displacement to the left. And in the areas where we have the higher displacement in lateral direction, we're going to have these very high bedding reactions, but the lower we go, the lower these reactions are going to be. And you know, this is logarithmic, so it looks a little bit linear here, even though it's basically decreasing quite drastically over the depth. And this is also like these cues are very important to verify that your software creates these, that our software creates these results, because with these visual cues we can already confirm that we did the right calculations. Okay, we have the same for the shear forces here. So this is the displacement lateral in meters. In this example, we have a maximum displacement here of around about 0.012, right? Which will equate to 1.2 centimeters roundabout. This is the maximum displacement for this scenario under the forces that are also being equated underneath here. This is the graph for the shear force, for the lateral forces inside of the pile, how they develop over the depth. Remember, this is a spring-beared system, so there's like springs all over the pile, and it's 1,000 springs. So this is basically how the internal horizontal forces will basically be displayed over the depth. And then the next graph is the moment, the bending moment. You have the zero here, basically you would have the maximum here. And you can use this to play around and understand this calculus a little bit better and get a feel for the results that it generates, and understand a little bit better if you have some sort of tool to play around with to just see like how different input parameters are going to change the results of the calculations. Okay. Great, so now let's jump into the research paper. So this paper was developed because at the current moment we are developing a very cool tool that is going to be partly like a management tool for piling foundations for the entire progress, but also a very important data science tool, because the more data we can gather over piling foundations and about the documentation aspects of it, about the machine protocols that are generated and the data that we can scrape from this, in comparison directly with the results from the design stage, the better we can in the future design piling foundations. And especially in maybe like 10, maybe 15 years, when many of these things are going to be evaluated by not only data scientists, but also by AIs. We want to be in a situation that we get the best quality piling foundations in any regard, in cost, and especially like in CO2 as well. And one of the foundation blocks that we use with this paper is to implement a very good horizontal dimensioning platform in order to embed this into any sort of Python-related software that we want to use. And one of these examples is the Foundation Designer, which is a software that is a full 3D with 2D plotting capability software for piling management mainly. We can do all sorts of cool things about piles, but what we couldn't do until now is we couldn't be able to do horizontal lateral piling design for these piles. And this is why we developed this software. Okay. The idea is we want to take all of these properties of these piles and fully automatically get sort of what we showed you earlier, these graphs and the evaluation of the horizontal capabilities of a pile, and then automatically find algorithms that can help us to find the right sort of rebar cage, the right sort of reinforcement for these piles. And this is what this paper is about. Also, a second very important thing is that obviously we can go ahead and this is some question that I get asked quite frequently is, yeah, but why don't you just use finite elements? And obviously in finite elements you can do a lot of cool things. You can get a lot of very accurate results, and you can get a very profound understanding of the environment that you're working in and how possible interactions between pile and soil work. However, this is very complicated and not really the advantages and disadvantages are, in my personal experience, in my personal opinion, not really practical for everyday use. Because if you have a project that has maybe, let's say, 7,000 piles, like a big logistics center, a big power plant, or whatever you're building, like a big data center, then basically you have hundreds, thousands of piles. And if you want to model like especially in inhomogeneous soils, so in very different soil conditions, each pile, and get the results, you will see, if you do this, that it will probably not only will take you increased a very, very big amount of time, but also it will take you a lot of human resource, and you will introduce a lot of additional work and additional error, because it's just going to be way more effort and way more complicated than just use more simplified approaches to it. And the level of accuracy and the level of results that you can expect is not going to be increased very well. It's mainly going to just consume more time and more workload for the people that are involved, without really generating any measurable benefit. And I'm really happy to run this experiment. So I'm always trying to be someone who owns his words. So if somebody is up for the test, how long something like this really takes, I'm really glad to do this experiment. And I'm not going to be the person that is going to do a finite element model for like 8,000 piles. But if somebody is willing to do this just in the name of science, then I'm gladly providing my help for this experiment here. And I'm also, obviously, I'm going to do this for free, because it's just unthinkable. Like, I can just shake my head off the idea that somebody would actually like do 8,000 piles in finite element models like this, because it's pointless. It won't generate. It will be a waste of time. So, and because of that, we need something more simple, but also something that can be used for more broader application purposes. And what I mean by this is that a lot of norms, this is an excerpt of a German norm here, like a German guideline, technical guideline for the design of piling foundations. And this is called the, how would you say that in English? It is the principle, the method of bedding modulus, and the way that it works is you have the bedding modulus, the subgrade modulus, and the way that you evaluate it is you have different subgrade moduli over the depth, and then you would evaluate the deformations of the pile over the depth, and then you can get from there also the reactions of the pile. The big disadvantage that this has, this is a brilliant method to do this if you have multi-layered soil even, but the problem is if we have a scenario that looks like this, where you have basically this would be like a pile wall for, maybe you have an excavation and you want to save the perimeter of the excavation with driven piles or with boring piles. Then the problem that you have is you cannot use this very well in this more versatile situation, because you can obviously use this method to get for the lower part of the pile with a standard deformation at the top. You could use this even. However, for the rest of the pile, in the areas where you have active earth pressure that is going to be loading the pile from the side, and also with the limited deformation here that you have to consider of this nail that is basically keeping the pile anchored in the surrounding soils. This is a more sophisticated sort of calculation that you would have to do. And for a calculation like this, you cannot really use this method well. And there aren't really methods to do these things. Then what people do in the field is basically they come back to something like this and they start to like work with very homogeneous soil situations, which basically makes this entire purpose of the finite elements worthless again, just due to the fact that they really don't know how to calculate stuff like this. And calculations like these, if you want to make them by hand, especially if you have shown it with like thousands of springs, would be for a hand calculation or anything that is like semi-computable. It's not a good recipe for success. So considering all of these three points, we had this idea to use the direct stiffness method to then develop this like an algorithm, a software that we can use to determine the internal reactions of a pile. So in stage one of this is just going to be like the publication for the main algorithm and the way that it's built. And this is going to be very versatile to be implemented. We took a huge emphasis on object orientation of these classes, so that it's usable and that obviously it's open source. So you can really take this. And use it for your own software and your own purposes as well. We also thought that it would be great to have some sort of video to go through it, to explain it a little bit in a little bit broader sense, because I know it from myself that it's always easier to just have a video and watch through it and follow like what the person is explaining, get a little bit more background information to just be able to digest it a little bit better. I just point towards the disclaimer in the beginning really quick. So it would be very nice if you decide to use this. Take a look at the license statement. Please provide a link to our website if you license it, and make sure that you mention us and that you give us the appropriate credit to this work. Okay, so now really quick, direct stiffness method. The way that it works is basically you have a system and you divide the system into elements, and these elements, then you will take a look at their individual stiffness matrix, and then you try to describe the entire system with the help of like all these small elements and their respective stiffness matrices in a general stiffness matrix. And then you have a stiffness equation where basically the entire system stiffness equation is to be determined with the unknown forces of this or unknown deformations, not unknown forces, unknown deformations of the entire system. Basically, which gives us a linear system of equations. Obviously, we can also do this non-linearly, but we get to this in a minute. And then you can solve this, and with the local stiffnesses, you can always go back to the deformations and then re-evaluate your internal forces. And so this is what the way that we do it. Just a simple example here. We have a pile here. That we have three springs here, which gives us two elements. So we cut this here in these elements. We call it element 1 and element 2. And if you look at the main system, this will be all the reactions that are possible in the system. So we have some sort of bending here, we have a horizontal deformation here, we have a vertical deformation here, and these basically we have in all of these places. So if we cut these elements in element 1 and in element 2, and also these springs away, then we have 3 of these reactions in all of the nodes of each element, and the same applies for the springs as well. Obviously, we can reduce the complexity of the system, because we are not really worried and concerned about the vertical forces in this place, because the vertical deformations are going to be very small. And when we talk, for example, about vertical loading and eccentricity, we can also describe the eccentricity at the top as an additional moment. So we can always catch eccentricity at the top with the leverage of the eccentricity times the normal force that is loading the system vertically, and then describe this as an additional moment, and then just we add this at the top node, so to speak. And so vertical is not really a point of concern here. Also, EA is always going to be very, very high. So we just, we use for simplicity's sake, we're just going to say EA is infinite, and this is going to be the end of it. So vertical forces and vertical deformations are not part of our concern. And so we're only going to have to think about horizontal and moment reactions here. Same applies for the springs. In the springs, we know that also the bearing reaction of the spring is going to be 0, and this is due to the fact that we use the spring to describe the soil. So at some point when the soil, when the elasticity ends of the soil, basically at this point you have 0 deformation. So this is why we call it 0 in the end as well. This is the local stiffness matrix of a base element 1. So this is what the base element 1 looks like originally. We have always, I mean, you see this here. I hope I can zoom in. Yeah, this is always a stiff bearing, which will have a moment reaction, a horizontal and a vertical reaction. And there is also different elements. There is base element 2. Base element 2, base element 2A, 2B, I think. But in this, just because it's also easier to compute and to explain, we're just always going to use this so that we always use the same stiffness matrix for each element. And just a little disclaimer, it's really important for a calculation like this that you simplify it as best as you can. So that we really think about like which are really the deformations that we have, where we know that we have some unknowns, and which are the ones that we might not be able to use, because we can cancel these out of our stiffness matrices in order to drastically reduce the level of computing power that we need in order to compute the solutions. So one of this is to also think about the length. So obviously, when we have a system like this, we want to make sure that like we divide the spaces between the springs equally, so that all of the elements have the same length. So that I just have to consider one length, which makes it a little bit easier. Okay, perfect. So this is the base elements 1 stiffness matrix. And the way that we can introduce this simplification is we just cross out the n dimensions of this equation. So we just cross out the n here, and then the entire row here, this entire row here, and then the vertical rows as well as the normal deformations of the deformation vector. And this leaves us with the simplified version of this, which is going to be a 4x4 matrix. For the feather, for the spring elements, it's going to be kind of the same. In this case, since it's only 2x2 and we say this is 0, basically what will happen is it's just going to be the vertical force is going to be C times the deformation. Okay. And the next thing we can do is, in this method, you can consider 2 sorts of vectors. It's going to be the element vector and the node vector. And since there is no loading apart from the loading of the top, basically what we can consider is we can say, okay, Fe is 0 because there is no loading on any of these elements, and it's just going to be the node vector. And for the node vector, it's even easier because also like in none of these other nodes there is going to be any forces attaching. It's just going to be top loaded. So at the pile top we're going to have some loads that attack. So the entirety of the load vector F is going to be, if Fe is 0, it's just going to have F equals Fk, and Fk is only going to be H and M, and the rest is going to be zeros. And this has the same dimensions as the main stiffness matrix with all of these reactions. So 1, 2, 3, 4, 5, 6 is all of our unknowns, so we have to have as many of these node reactions here. Perfect. Okay, I hope that you understood it until this point. Make sure that you really try to understand it till this point as best as you can. Obviously, if you have questions regarding this or feedback, then make sure that you write us an email. The email address is info@deepfoundationdesign, deep-foundation-design.com. Okay, so now we can build the stiffness matrix for the entire system, which is going to be describing these this vector here, which is here f, and we have f1, 2, 3, 4, 5. This is going to be h. This is going to be m, and then we have the unknown deformations at these places, because this is what we're going to be wanting to calculate, these unknown deformations here, and the way that we explain this is actually, so while I was creating the video and I was starting to explain, I realized that this is too abstract to explain it without doing some drawings. So I will do my best here to just give you an idea of how this entire thing works. So think about this as our first element. So you remember we reduced the complexity of our first base element like this, and what we do now is we take this as our first element. So the first element's stiffness matrix look like this, and what we are going to do now is we have remember we have these 4 reactions, and we now look at this drawing here in the beginning. So we look at the first element here. And we're trying to figure out, like, okay, this is the global reaction 1. Let's maybe take a different color here. This is our global reaction 1. This is our global reaction 2. And we have to assign these and compare them to the local element that we cut out. And what we see here is, okay, that these are basically the same in the global system. And so when we look at the global matrix, basically what we're going to see here is that at the position of the global matrix we have from our first element, this is why it's in the box here, first element, the first entry in the first row in the first column. That's what this means. What we also see is that there is something added, and this is a spring. And this is also being explained here because, you remember, we have the spring here. And so the first part of the spring here, this is also going to be here at the first reaction 1. Okay, so second reactions here, we already said these are 0, so these are none of our concerns, and this is why we just say here, you remember, this is the first row, first column of the spring, and this is why we just see here, okay, the first row, first column of the spring, first spring, basically. And with the springs, I mean, with the base elements, they're going to be basically all the same, and this comes in very handy later on. Okay, so let's now look at the second element and at a node condition. This is basically our second element, and as you see here, these overlap. And this is because what we see here is that we have, for our first element, we see, let's go back to the red, this is the first element here. We see that these nodes of the first element are the unknown reactions 3 and 4 of the global system. But what we also see is that at the very same position, we have an overlap with the base element 2. And this is the starting nodes here. So the starting nodes of element 2 are at the position of the global unknown 3, and the 2 is going to be here where the 4 is. It's a little bit complicated. I hope this explanation works. And with this, we jump back into our matrix now. So basically what we see here is this overlap. It's like we have the first elements. Let's try something here. First element, the 3, 3, which is going to be this one here, 3, 3. And what we have is the second, let's make this in blue, the second elements 1, 1. So let's go back here, and we see 1, 1. They overlap. These two are both the horizontal unknowns, the horizontal deformations of the 3 of the total system, and here of the local system it's the 1. And then what we also see is that we have our spring 3. Maybe we can do this in another color. That it's going to be here as well. So this is also going to be here. And we have to add this as well. So we have our second spring here and our first entry, first column, first row. And all of these have to be now added together. So the way that this works is we go here into the stiffness matrix for our first element, and we take this one and we add this to the 33 entry of the second element. And since both of these base elements have the same stiffness matrices, we can just add these two together. And what you see now, and this is really cool and really handy, is that these basically are the same entry. So if you align these in this fashion where you have this sort of effect where you're just always going to attention in this fashion, basically you have very strong symmetry effects. And the way that we can consider these is we can see here we have any sort of element, and we can always say the 1, 1 and the 3, 3 is going to be the same. We can say that the 2, 2 and the 4, 4 is going to be the same. And what's also really useful is that the 1, 2 and the 3, 4, that they are having different, how's this called? That's basically this is minus here, right? And what this does is basically that these cancel out. That these are basically, we don't have to consider these are going to be 0 in each row and in each column. So this is very useful, and this is the way that we build these sort of matrices. And obviously this is, in my personal experience, I really had to do this quite a couple of times by hand. And obviously you can do this for very complicated advanced systems where you have rotated elements and stuff like this. And then it gets very, very complex because there's also transversed matrices where you really have like the rotation angles. And I mean, the complexity increases with the complexity of the system. Like a pile is not a rocket science. A pile is just a vertical pile element in multi-layered soil. It's yeah, and this is a very simple system that we describe here. So it's kind of still understandable, but obviously the more complex systems you have, the more complex it's going to be. But I hope that was easy to understand. And so here we see this in a simplified form. Here we see, for example, that we have these factors introduced because we can simplify it this way. We can see that these cancellations have been taking place. And yeah, we have now the most simplified version of this matrix possible. So now we can substitute all of these values in there. We can do this addition. We can cancel out these values here, and then we have the final linear system of equations. And now the way that it works, you just solve the system of equations, and then the way that you can get your internal forces is you take basically this this principle from the beginning, and you basically reverse engineer it. And the way that this works is now you have all of these. Now all of these are not unknowns anymore. Now they are knowns. So the way that you would calculate the forces, as you see, where did I put the vectors? As you see here, the way that you get these element vectors now is by just taking these unknown forces and multiply them. So this is the unknown deformations that you have, right? This is what we calculated by solving the system of equations. And the way that we get now the internal forces is we just multiply this vector of unknown deformations for each element with their base element, and this is going to return us the internal forces. And these internal forces we can then plot into any sort of diagram here. And this is just an example of this like very simple example how this would look like with the displacement in lateral direction and shear forces and the bending moment for here 3 springs, and basically load we said it's going to be 1 kilonewton, and the moment is going to be 1 kilonewton meter, and so on and so forth. So this was quite a lot to digest. Now we have to, when we introduce the system, and you already can think about like many open questions that are now like, for example, how do we calculate the stiffness of these springs? Yeah, because until here everything sounds really plausible and logical, and from the math aspect not really complicated. But how do we determine now the stiffness of these springs? Right? Especially if we have like thousands of springs. Like, how do we really determine these? And first of all, what we need to do in order to think about it appropriately is really understand what these springs are. So we have a pile, and basically with a number of springs, we sort of, but not really, divide this pile into segments. And the way that you can imagine the spring is the interaction between the pile and the soil in this segment. So basically you have a reactive length, like an element length, and you have a reactive surface. This is basically the area at which the pile reacts with the soil, which will be looking something like this. And what we can use and what is often used in geotechnical reports is the elasticity modulus. And the elasticity modulus, there's something that's called, I don't know how it's in English, but in German we say Ödometerzelle, which is basically you put the like a sample of soil, you put it into this small little box. You have a drain for like the water, if there's like water in. Basically we have we add a force on the top, like you have like the stamp, and then basically the stress that you add and the deformation is going to give you the elasticity modulus. Here you'll see how something like this looks. And we can use this for our advantage, because this is literally what we're talking about when we talk about horizontal displacement. We have this reactive body, we have the soil, and then we press the pile into the soil and we want to know what sort of deformation we have. And the way that it will deform can be described over this elasticity modulus. Or in this case, we are going to just call it stiffness modulus to be more precise. Here we see this, what I tried to draw, like how it works for the pile. Basically, this is the area of influence for each spring element. All of them should be evenly spaced. This is very important for this, otherwise it's going to unnecessarily increase the level of computation that you're going to afford. So the next thing that you can think about is okay, how does this reaction actually looks? Because obviously, like when you have a round pile, it's kind of really not intuitive, like how this reaction is going to look, because at here you're going to have a lot of shear in the areas when you press the pile, and if this is lower than the internal angle of friction, basically you will have zero shear. And then from here on, you're going to also, because you're not going to just push the pile away like this, you're going to have some sort of spatial reaction of the soil. And the way what we basically do here is we just say, okay, we're just going to use the entire diameter of the pile, and we're just going to assume a very simplified version of this reaction for, and this is very important, for determining the spring stiffnesses. Why do we do this? Well, this is obviously going to give us some sort of higher results, but on the safe side, it's always to do something like this. Because this is really, and on the resistance side, we're going to use this just to add some extra added safety, not because we want to increase the level of safety in a very uneconomic fashion, but simply due to the fact that soil is inhomogeneous and not all the soils behave exactly like this. And so we really want to make sure that we are on the safe side when it comes to our calculations. So what this basically does, it will actually decrease the spring stiffness that the results are going to generate. This would increase it. And so we want to always make sure that we are like making reasonable decisions when it comes to the resistances and the forces that we calculate our systems with. So now the way that we are going to be calculating the spring stiffness, we obviously can calculate the tension at this very spring by just dividing the normal force at the position by the area of influence of this spring. This is going to give us the tension. Obviously, we don't know this yet, but we don't have to. It's just the way that we can calculate it. For the N, what we can describe N as would be the spring stiffness here times the displacement. This is basically the spring force at this very position. Now what we can do is we can enter this here, which would give us Ci times WCi by ACi, which is going to be the force. And what we can also consider is that we can also describe the stress as basically the elasticity modulus, the stiffness modulus of the soil, times the percentile or per mil, how's it called, the differential between the, basically the length of the body of soil times the displacement that we already have. So in English, it's going to be this. I hope that you understand this. I mean, if you watched the video until now, you probably understand what I'm talking about. It's just the lack of English at this point. So next up, what we can do is we can rewrite this here. This is basically delta L by L. We always look at it in 1 meter, so we don't take like 25 meters area of influence of the entire system. It's just we're going to say like simplified, like it's 1 meter, because also the deflections are always going to be very small. We are not going to see like deflections of like 0.3 meters. It's going to be like always in area of a couple of centimeters maximum. So like calculating this for 1 meter really is something realistic that we can do here to substitute to really decrease also the complexity of the computation. So now what we can do is we can bunch all of this together. This is what I talked about in the beginning, and then we have the elasticity modulus here. We have basically this is the left side, the right side of the Hooke's law, and this is basically the friction from all the way up here that we just where we just added this in, and then we arrive at this equation. And now what we can do is we can basically say, okay, these are going to be the same. Like the lateral displacement of the spring is going to be the same lateral displacement of the soil, right? And so we can basically cut this lateral displacement, which is unknown at this point. We can cut this really out of the equation, which leaves us at the spring stiffness divided by the area of influence of the spring is equal to the stiffness modulus times 1 divided by 1 meter. And we can obviously now multiply the area of influence of the spring, which then in the end is going to be Ci, the spring stiffness is going to be the area of influence of the spring times the stiffness modulus of the soil. And the entire thing is 1 by meter. When it comes to the units, obviously what we can say is the stiffness modulus is kilonewtons divided by square meters, and the ACI, the area of influence, is going to be square meters, and then we have the 1 divided by meter due to this delta L by L. If we kill the delta L, we still are left with the L, which would be 1 meter. So what we have is we cancel out the square meters here, and what is left is kilonewtons per meter. So per meter of displacement, we are going to have E times A is going to be the spring resistance. Very, very logical concept if you think about it. Okay, so the linear soil layer model. This is the way that this soil layer model is structured. I'm not going to jump into this because this is very trivial and not really complicated. It's just the way for the computation that we're going to structure the soil layer model. It's just we have a soil layer 1, 2, 3, 4, and these need like the starting coordinates for the depth for each of these. That's a little bit like tricky with like we have to think about like how we enumerate all of those. But this is just object-oriented programming at this point, and not really complicated. Earth resistance is something very important, and this is something that we talked briefly in the beginning. And remember where we talked, So the earth resistance, passive earth resistance, is something really important, and in order to facilitate why it's so important, we look at just one of these sample calculations from the tool. What you can see here is that you have in the fat gray line is going to be the passive earth resistance. This is what this is about, this chapter. And the slim black line is going to be the actual stresses between the soil and the pile. And the way that you can think about this is when you press the pile against the soil, then at some point, like the stress against the pile and the soil is going to be higher than the passive earth resistance in this area. And what ends up happening is you basically push the pile, pushes the soil away. And then our model doesn't work anymore, because you see this here. If like our deformations here are too high, at some point what's going to happen is you're going to take all of this soil here in this area and you're just going to push it along the angle of friction upwards. And then basically it would be not really realistic to assume that there's any sort of spring reaction here, because the soil is already being pushed away, and then obviously it doesn't have any spring resistance. So this is very important that we keep this in mind, and this is the main reason why we do this sort of proof in the end, to really verify that basically this is the verification that our model that we use to calculate it is actually valid. Because if we cross over this line, basically we have to make some adaptations on the soil layer model, or on our model in general, or we can just assume, okay, the forces that we have in the system are too high. Not only are the internal forces too high, but also the stress that is going to be generated, even if the pile could bear these internal reactions. It will just push the soil away, because our soil is not good enough in the top layers. Okay. Perfect. So this is very important, but I think this will be too much for this video to evaluate this. I mean, all of these things, how to evaluate the passive earth resistance, is a topic in and around itself. I could talk for hours about this, and I think I spare you this in this video now. But basically, if you're interested in this, then I can make a second video explaining more about the passive earth resistance. But this is only if this is really interesting for you. I think it's only important for you to understand how this works in principle, and to just make sure that once you play around with this, that you always remember, okay, if my tension between the soil and the pile exceeds the passive earth resistance, then basically it will just push the soil away, and then there is no point in, then obviously our mathematical model to describe the system is just outright wrong. So this is the only important thing here. And yeah, there's some graphical ways on how to get like some of these. What we use is these passive earth resistance. How is this called? These are basically values that you use to calculate this, and there's graphical principles how to calculate them. There's mathematical principles on how to calculate them. This is what this section of the paper is about. And yeah, then the last chapter is basically creating this in Python. And I think if you're interested in this, I can also make yet another video about this, because there are some very interesting and very useful features that you can use. You can use the inter P1D function which is a very, very powerful method to interpolating. It's not only available in 1D interpolation, but also in ND interpolation, which can be handy for a certain amount of very complicated mathematics. And certainly in design engineering, I use this quite frequently. And if you're interested in this, I can make a video of the programming of this as well. Yeah, I think this is going to be it. Maybe just I didn't know that I included this here in the paper, but what I also did while I was programming this is I always also returned myself the stiffness matrix, the global stiffness matrix, just in order to make sure that I can go back to my paper and just look at the elements, how they look. Let's make this red again because we have been using red before. So remember when we were talking about the base element 1 and how there's certain things that are recurring here. So basically here we see at the first node we have the, wait, I think that's not correct. Okay. What we see here is that we have the E11 of the first element, and from the first spring. The first spring is going to be always like, obviously we programmers, we like to start at 0 with the first number, so the first is always going to be the 0, second is going to be 1, and so on. It's a little bit confusing, I know. But then what we're going to be seeing here is we see that we have these, that we have this beautiful overlap here of all of these following elements. Yeah. And now if you look closely, what you can see here is that we have these entries that had been cancelled here, which is pretty useful. And you see that here as well, cancelled, cancelled, and so on. We always have like the 2 times the E11 because the E11 is the same as the E33, as you remember, and we always add also these springs, and we basically do this till the end of our system. So this is always something that I do in order to verify that what I'm actually calculating and what I'm programming, to put this in a visual context, just to confirm by just having this output that my stiffness matrix is correct and that the results of the software are going to be proper. So I hope this was interesting. Basically here in the end it's just going to be the results, the discussion of the results, then a little bit on Python, a little bit on how like the nonlinear approach actually could work. So to use the nonlinear elasticity modulus, because we just used the linear elasticity modulus or stiffness modulus here, and then basically the entire code of the software. So I would be really happy if you have feedback or if you have criticism. The email address is info@deep-foundation-design.com, info@deep-foundation-design.com. And yeah, I'm really looking forward to what you think about this. If you have any questions, if you want me to do further elaborations on the paper, then let me know. And there's certainly also coming out videos on the matter in German, and also the follow-up videos are going to be there anytime soon. So I hope this was helpful, and goodbye.